All right, good morning, everyone. We are going to, so our roadmap for today is we're going to talk about some logistical issues. Then we are going to look at the solutions for exam number two. And then we are going to move into some new material for the rest of today. So, first of all, and half of you have probably heard this already, we're going to end up moving exam 3 back by a week. I will also make an announcement to this effect on Web Campus, but um, we will be taking our exam uh, on the 12th. Is anyone super broken up about that? Because if so, we can definitely take it on the 5th, but the plan is for the third exam to cover 11, 12, 13, 14. 13 and 14 are going to be covered very briefly because you've basically already had them in general chemistry. And depending on so today we're going through chapter 12, but um, depending on how we do. Yeah, so anyway, that'll be our current plan. We'll take the test on the on November 12th, um, which will give us the 5th to cover chapters 13 and 14. The final is going to be semi-cumulative. So on the other exams, the structure has been something like, here's 10 questions, pick 6. That is also how the final is going to be structured. There will be one question from each chapter, except for 15, which will have 2 questions. And then you will pick which questions you answer. All right. How does that feel for everybody? Is that all right? Yep. 2 questions from chapter 15, 1 question from every other chapter, and then you will pick. I don't know, we're going to have a full 2 hours for the test, so probably 8 questions. I haven't done the math on that yet. And yeah, they'll be exactly the same style of questions from the previous exams. They will be heavily inspired, if not directly drawn from the textbook. It'll be the same time per question, basically. That's how I'm good. I haven't done that calculation exactly, but basically I've been expecting you to do a question in about 15 minutes. And so for a 90-minute test, that comes out to about 6 questions, and so for a 2-hour 2-hour test, it comes out to about 8 questions. Megan, I have no idea what next semester is going to look like yet. That is, yeah. Um, but I don't know. I guess I don't know. That's a question I haven't settled to my own satisfaction yet. Um, I'm teaching 152 this semester as well, and I'm experimenting in my 152 class with not having tests at all and just having a quiz every week. I have no idea what's going to be online or in person. Um, and frankly, since I'm a part timer at UNLV, I have no idea if I'm going to be hired to teach next week or next semester. So if you think I should, definitely give me a nice review when when at the appropriate time. But yeah, adjunct professors are not guaranteed a job from one semester to the next. Thank you, Chad. That is the best compliment I've heard all week. Um, so yeah, that's where we're at. So I don't know. Yeah, I don't know anything about next semester. That's the long and short of it. Okay. Do we have any other logistical questions before we move on to test solutions? Exam 2 will be graded next week. I'm going to use our day off next week to catch up on all my grading. That's right. There's no class next week. I guess that's worth mentioning. Yeah, for Nevada Day next week, there is no class on Fridays at UNLV. Okay, well, Abigail, that just hurts my feelings. That's right. The 29th, there is no class. So, so get some sleep, catch up on your studying, check in with your friends and family you haven't spoken to in weeks. Yeah, all that stuff that you do on your days off. One of my colleagues is doing an experiment where instead of grading the exams himself, he publishes the rubric and has everyone grade their own exam, and then he reviews their work. I am not 100% sure that's a good idea. The ultimate goal is to see if people are to see if people can incorporate feedback and look at themselves honestly. So I mean, ultimately, he takes the exam and the grading that the student did for themselves and decides whether that's appropriate, reserves the right to adjust it. But he says that for the most part, something like 75% of the class assigns themselves the grade that he would have assigned them. All right. Let's go over the exam questions. Question 1 is an energy conservation question. Cars are among the things that I really can't draw, so I'm just going to make it a box. So situation A, we have a box at the bottom of the ramp. Its velocity is 8 centimeters per. Its velocity is something at the bottom, and its height is 0. So this is situation A. Situation B, the car is at the top of the ramp. Velocity is only 8 centimeters a second, or 0.08 meters per second, and the height is 1/5 of a meter. Now, there are no external forces happening between A and B, so we get to say that the energy at A equals the energy at B. So at A, the energy is all kinetic. At B, we have partially kinetic and partially potential. The M cancels out of everything. Alright, so 2GHB, so G is about 10, so this first term is about 4. And this second term is actually tiny in comparison. 0.08 squared is what? 0.00064? One more zero. No, not one more zero. Okay. So this is approximately just 4. Which means that the speed at A is going to be 2. Okay, questions or comments?
Did we square root? Oh yeah, we did. Sorry.
1.98, also a perfectly acceptable answer. That's what you get if you plug in 9.8 for G instead of 10.
Would you lose points if you drew a picture that contains both A and B? Just one picture, but both situations at once.
Nope, that's perfectly fine.
Perfect.
So I have done a first look through the test. I haven't assigned grades through them, and it looks like about a third of the class didn't draw any pictures at all for any problem. So if you drew a picture, I will give you props for it.
I misinterpreted the question and I thought the ramp was 20 centimeters long, so I didn't figure out the height. Would I lose points for that?
Well, I would have to look at how you worked it through, but if you assume that the 20 centimeters is the length of the ramp, I don't think that there's a way to solve for the initial velocity?
Yeah, I didn't. I just put the square root of 4h plus 1.6 over 0.2.
Oh. Well, you won't lose too much. Like maybe 1 point.
Okay.
Maybe,
Okay.
a point or two depending on how much work you showed. But if you misinterpreted the question and then, bowled ahead as far as you could go, then, I give you credit for that. That's still good work. All right. Any other questions or comments about this problem? We're going to go on to the next. Two and three are hard. That's valid. Question 2 is a trick question. It doesn't matter what angle you throw it. So situation A is up here. Situation B is down here. And you could have done this problem via either kinematics or conservation of energy. So I'm going to show you both. For conservation of energy, there are no external forces between A and B. Also, we're going to say up is positive. Energy at A equals energy at B, because there are no external forces. That means that we have 1/2 m VA squared equals plus MGHA equals 1/2 m VAB squared. Or, whoa, wow. VB squared. Okay. And if you take a little closer look on VA squared here, right? If our velocity goes something like this, so there's VA, so down here is VA cosine theta, VA sine theta. You will notice that the actual magnitude of the speed, which is what kinetic energy depends on, doesn't have a theta in it. Only the x and y parts have a theta in it. And we end up getting a result that looks almost exactly the same as the result from question 1. And yeah, there are no thetas in it. So we just say no theta means angle doesn't matter. If we used kinematics, then instead we can say, well, our initial position is 0 in the x direction, 10 in the y. Our initial velocity is VA cos theta, VA sine theta. Our acceleration is just gravity. Time we don't know. Initial final position we don't know. But using kinematic 2, we can say that the final velocity in the x direction equals the initial velocity in the x direction plus acceleration times time, but acceleration in the x direction is 0, so our x velocity doesn't change. In the y direction, we can use k3, and we can say the final velocity in the y direction equals the initial velocity in the y direction plus 2gh. So our final speed, right? Our final speed will be, we use the Pythagorean theorem once we have the parts. It should be VBX, VBY. Okay. If we look at these first two terms, VA squared cosine squared theta plus VI squared sine squared theta, if we factor out of VA squared, we get cosine squared plus sine squared, which is 1. So we get the same result as we did in pink, and once again, once we're down at the end of it, angle doesn't matter. Okay. I know there's a lot of does anyone have a question about this that I didn't answer as I was going through it? Felt like you were being pranked? A little bit. Okay. Can we go on to the next question? We're all a victim of physics, Megan. Forces that we cannot control. All right, so question 3 features the same battleship from exam 1. So it's firing the same shell, it's firing it due east, I think even with the same speed. What's the velocity of the battleship after firing the shell? And what we're going to use here, right, because this is not kinematics or forces anymore, like we're trying to think about this in terms of energy and momentum. So that's exactly what we're going to do. So we're going to try and solve this problem with momentum. So it's situation A. We have a battleship, bird's eye view, and yes, I am basing my drawing on the pieces from the game Battleship. Initially, this thing is going north at a speed of 60 kilometers per hour. Situation B, we have the same battleship, even though for some reason I've drawn it a little fatter than the first one. We also have a shell which has been fired 500 meters a second to the east. And presumably, because of recoil, the battleship is not traveling due north anymore, but something off kilter. All right. However, momentum is always conserved. So momentum at A is equal to momentum at B. At situation A, or the momentum in the y direction is equal to m1 v1 ax. It's a lot of subscripts. We're going to untangle that in a second. That's why. Yeah. The only thing moving in the y direction at situation B is still the battleship. Right, so the battleship is M1, the artillery is M2. Right, so this is enough to tell us that the battleship still has the same speed in the north direction. So its north velocity has not changed as a result of firing the shell. In the x direction, however, At time A, the x momentum is 0. At situation B, we have the shell moving to the east, which presumably means then we have the ship moving to the west. Which tells us that the speed, right, during 2 steps of algebra, alright, we can plug in some numbers. The artillery shell is 1 ton. Its velocity is 500. And and then the battleship is 50,000 tons, which is the same as 50 million kilograms. So it's 100th meter of a meter per second. Not a lot of velocity. It's picked up in the x direction. Well, if you only dealt with the y direction, then I don't think you really engaged with the problem at all, right? Because everything that was really being asked is over here in the green. You could totally find theta. I did ask you to specify the velocity. So you could say something like the velocity of the battleship at B is equal to 1/100th of a meter per second in the x direction. And I mean, you've got 60 kilometers per hour. Convert that to, if you did only the x direction, then that's better. Since the y velocity doesn't change, I wouldn't even have cared if you converted 60 to meters per second, as long as you put the appropriate units on these numbers.
For this question, I use like the equation like m1v1b plus m2v2b equals m1v1a plus m2v2a.
That's exactly what's going on here. Yep.
Okay, but like when I solved it, I got like 16.657 for v1a.
Yeah, that is 60 kilometers per hour converted to meters per second.
Oh, okay. Thank you.
So when you are tempted to overthink a problem, remember that you don't like doing long problems, and I don't like grading long problems. So, like, we're really on the same page here. Nobody wants long, complicated problems on a test. If you use the Pythagorean theorem to get a number for the overall velocity, it would be approximately just 16.7. Right? Because the x component of the velocity is so small compared to the y component of the velocity that it only changes at 0.03 degrees. So So yeah, with any reasonable number of significant figures, you won't even notice a difference. You cannot always get away with not doing the Pythagorean theorem. However, in this case, so I ask you to specify the velocity, so you can, and that means it would be perfectly acceptable to write it as vector components, or it would be perfectly acceptable to write it as magnitude and angle. Either one of those is a perfectly acceptable way to specify a vector. Any other questions or comments here? Question 4. We're bowling. I saw some actually pretty excellent diagrams. At least a few people drew in all 9 pins and a bowler on the far end. I was particularly tickled by that. Let's see. Can I draw a bowling pin? I probably can't draw a bowling pin. So instead, I'm just going to draw a square or a rectangle. So this is going to be a side-on collision, probably. So if you've ever bowled, you know that you're not supposed to aim directly for the center pin. You're actually supposed to hit it on the side. That's the best way to get a strike. So situation A, we have the ball coming in, the pin being stationary. Situation B, we have the pin flying off at an angle of 85 degrees. And the ball presumably has been deflected downward. So the pin is deflected by 85 degrees. The bowling ball is deflected by some amount. Alright, and this is situation A. This is situation B. What color have I not been using today? We'll go with... do a nice dark blue. There we go. Okay, so we have a collision here. We know that momentum is going to be conserved. So momentum at A equals momentum at B. And just like before, I actually want to split this up into x and y components. So the momentum at A in the x direction equals the momentum at B in the x direction, and also the momentum at A in the y direction equals the momentum at B in the y direction. So in the x direction, originally we have m1 v1 ax. That's our 5.5 kilogram bowling ball and our 9 meters a second. the pin, however, is initially at rest, so it has no velocity at situation A. At situation B, it does have some velocity. So far, so good. And if we do a quick check of this equation, we check for the things we don't know. We don't know v1bx, we don't know v2bx. In the y direction, which will be a different shade of blue. Our initial momentum in the y direction at situation A is 0. Nothing is moving in the y direction, rather. And at situation B, we write down what we've got. Okay. And now we want to bring the geometry of the problem to bear. And also, we want to bring the geometry of the problem to bear. So this v1bx, right, is going to be v1b times cosine theta. And the m2bx is going to be v2bx is going to be v2b cosine theta. And at that point, or cosine 85 rather. All right. And we actually know everything in this term. We know all of these numbers. We don't know v1b, we don't know cosine theta. In the y direction, we're going to do the same thing, bring in the geometry. And again, we don't know v1b, we don't know sine theta. You do. I have some people are asking, is it 14.7? Is it minus 14.7? And that's going to depend, whether you get 14.7 or minus 14.7 is going to depend whether you let the negative direction be carried in this theta, or whether you put the negative sign in the front to indicate that you know it's going to be going downward.
Can I ask you a question?
Yeah, of course.
I don't know if that's the lab confusing me too, but for the y, I use sine 5 because that's I drew, the axes that where the y is, it's 5% away from the vector. Not percent, sorry, 5 degrees.
Away from the y direction. Mm-hmm.
Yeah.
So if you wanted to use that angle, you would have needed to use cosine 5 over here, because sine 85 and cosine 5 are actually the same number.
Got you. Thank you.
Okay. The y direction looks simpler, so let's start with a solution there. And I'm actually going to be, my tendency is to put this negative sign out here, because from the picture I drew, I know that I expect it to be going in the negative y direction. So I'm just going to indicate that in my equation. It's also perfectly fine to let the negative sign be carried in your theta. Just don't do both, and don't do neither. Right? Pick one. Little algebra lets us say that v1b is equal to m2 v2b sine 85 over sine theta. Plug that in over on the left. We get m1 v1a. What's m1? m1 is 5.5 kilograms. Oh, where is m1? Excellently spotted. Okay. We have some cancellation going on. Cancel, cancel. Cosine and sine together give us tangent. And at this point, I am content to plug in some numbers, because we have only one unknown, just this theta, and we want to solve for that theta. And in fact, this gives us theta equals 14.7 degrees. Once we have that, we can plug straight back into the light blue equation. And we just plug 14.7 degrees right there. Okay. Is everyone okay on how we got there? The second part of this question is actually the easy part. Is the collision elastic? Right? In other words, does the energy at A equal the energy at B? Right? So energy at A is 1 half m1 v1a squared. Does that equal 1 half m1 v1b squared plus 1 half m2 v2b squared? And that's just a plug and chug now. So on the left-hand side, 0.5 times 5.5 times 81. So on the left-hand side, we have 223 joules. On the right-hand side, we have a half times 5.5 times 9.1 squared. Yeah, so it is not elastic.
Did we have to show work to prove that it was not elastic?
You just got to plug in the numbers and show that they are not the same.
Oh, I literally just said this is an inelastic equation or collision.
Yeah, we need a reason for why we think it's inelastic, if that makes sense.
Okay.
So in fact, this is an explosive collision. Right? If you'll notice, the bowling ball was originally traveling at 9 meters a second. It ends up traveling 9.1 meters a second.
Dr. Wolves, for that one, I didn't do like, what I did is that I left the velocity, I left it in vector form. Is that okay? Like I put 8.79 comma negative 2.3 thing 09 or something.
Wait, say that again?
So what I did was I left that in vector form for the velocity. I just put 8.79 comma negative 2.309.
That's fine.
Okay, and also I said that the reason why it was I mean, you said that's inelastic.
Well, yeah, so elastic means that you have the same kinetic energy before and after.
Oh, well, I said that it's, or I don't know. I said because I thought elastic, if they don't stick together, then that makes the or the problem an elastic one.
That is, so not sticking together is a side effect of an elastic collision, but it's not the definition of an elastic collision. So sticking is completely inelastic, conservation of energy is completely elastic, and most things are somewhere in the middle.
Okay, so since I didn't, so how many points would I get taken off for saying elastic because do not stick together?
1.
Okay.
Oh, for the second part, I only compared like the first velocity, and I didn't, and then on the right side, I didn't do like the 1/2 m2v2v. So, but then I show like the two like first velocities were like not equal. So would points be taking off for
Well,
that?
yeah, the velocities will definitely not be equal. The question is, are the energies equal?
Yeah, like I just did like that 1/2 m1v1b squared equals 1/2 m1v1a squared, and then it showed like they were not equal, but like I didn't do like the 1/2 m2v2b.
Oh, that's true. So if the first two terms aren't equal, then adding another term on the right-hand side to make it even bigger definitely won't make them equal. So that's reasonable.
Okay.
So the reason why this fails, right, is actually because bowling balls are a little more complicated. So by the time a bowling ball hits the pin, it's not sliding, right? So only the first 2/3 of a bowling lane are oiled, and the last third has no oil. So the ball stops slipping and starts rolling. So the reason why it doesn't look like energy is conserved is because there's actually rotational kinetic energy on the left-hand side as well, and then not on the right-hand side. But that's just because I'm a bowling nerd, and you didn't have to know that. Well, friction would be a good explanation for why there's less energy after the collision. But here there actually appears to be more energy after the collision, which is weird. All right. We have someone holding a plank. For those who came to office hours, this is real similar to the pole vaulter question. So if you're carrying a plank of wood by one end, right, the entire thing is 3 meters long. You're exerting a downward force on the end of the plank. You are exerting an upward force with your other hand, a little bit in from that, and that's 0.5 meter. Also, we have the weight of the plank, and the weight of the plank is, of course, going to act halfway from the end. Like, it's going to act in the middle. Yeah, the center of gravity. All right, so we need to do two kinds of analysis here. We need to start out doing a force analysis. For a force analysis, we will consider up to be the positive direction. If you are actually holding this thing and not dropping it or throwing it, then the sum of forces in the y direction has got to be 0. So that means that F2 equal F2 minus mg minus F1 has to be 0. So F2 equals mg plus F1. And we can't go any further there because we don't know F2 or F1. We're going to need another piece of information to finish solving that puzzle, which we can do because we know about torques. For torques, we're going to say that counterclockwise rotation is the positive direction. And if we are holding this thing steady and not twirling it like a baton, then the sum of torques has to be 0. And we can choose wherever we want our center of rotation to be, or axis of rotation to be, because if it's not rotating about any point we choose. There are a couple of natural choices for where to put the axis of rotation, right? And I think those are probably the 3 best choices. For my purposes here, I'm going to put the axis of rotation on the end, because again, if it's not rotating at all, it's not rotating around the end of the plank. So then the torques we have are going to be F2 times its distance, which is half a meter. And that's going to tend to cause a counterclockwise rotation, so it's a positive torque. The weight is going to tend to cause a negative torque, and it's going to be acting a distance of 1.5 from the axis of rotation. So that implies that F2 is equal to mg times 1.5 over 0.5. In other words, 3 mg. Since the mass of this thing is 30 kilograms, which is actually a pretty heavy plank. So you've got to be a real Chad to be lifting this thing by the end. No offense, Chad. Right, and then the force analysis we did earlier. Why did I write not very efficient person? Because this is a terrible way to carry a long piece of wood. You should just carry it on the middle. That way you would you would use less force. Yeah, 882 and 588 sound about right for if you use 9.8 as gravity. Right? An efficient person would carry the plank in the middle, or they would carry it vertically. So questions, comments on this one? Let me pull up the figure that they are referencing. Alright, so this diagram, do you think we could copy textbook images from our diagram? I mean, if you're preparing an electronic file for submission, like you're definitely capable of doing that. I mean, I've taken the stance basically that since this is an online class, you can do whatever is available to you as long as you have the test in on time. So, That's right, Jasmine. You have to alter or redraw this diagram because we're asking about 75 degrees, not 90 degrees. So right now, the forearm is at 90 degrees. We are interested in what happens when your forearm is not level. So this is my drawing of an arm. We have the bicep force being pulled straight up. Still 4 centimeters. We have the weight of the biceps, or weight of the forearm, still acting at the center of gravity. So the weight of the arm, and this is 16 centimeters. Thank you. And then lastly, we have the weight of the book. Okay. So in each of these cases, we need to determine what the angle between the forearm and the force is. Okay, so both of these are 75 degrees. And then the angle for our bicep, this angle is 75 degrees. Okay. So how much of these forces are perpendicular to the arm? So for B, bicep force, it's going to be well, I mean, for all of these, it's going to be sine 75. Is going to be the perpendicular part, because they're all 75 degree angles. Okay. So then we go to sum of torques, because we want to know how much bicep force does it take to make this, to make your arm stationary at a 75 degree angle. So sum of torques going to be 0. And again, we're free to put the axis of rotation wherever we want. Although, you know, maybe putting it at the elbow joint seems kind of natural. So our sum of torques are going to be, so our bicep is going to be producing a positive torque, because it's going to tend to rotate in the counterclockwise direction, and then the two weights are going to tend to rotate our arm in the counterclockwise direction, so they'll be negative. And I can't use B twice. I just noticed that. This will be T for textbook. Hold on, forgot the angle. In which case we just have to solve for B. Right, so the force that the bicep must exert, and here the 75, right? It's going to cancel out of everything. Which implies, actually, it's the same force as it was when your forearm was flat. Are you mad, Yusuf? Well, no, so a sine 75 cancels everything. So since we have a 0 on the left, we can divide everything by sine 75. All right, two problems to go. Oh, the final number? That's the boring part.
Dr. Wolf's.
Yes.
I used cosine instead of sine because it made more sense to me, and I think because I remember when I rechecked this, I think I got the same answer. Yeah, I got like 470.4, something close to Yusuf's answer. So would I get points taken off? Because to me, it made more sense to do cosine.
Cosine
And I
of
even
what, though?
Cosine of 75.
So cosine of the 75 will give you the quantity of force that's moving along your bone rather than perpendicular to your arm. So
Well,
that's not the quantity of force that's going to produce a torque. So
well,
yeah, you
because
could totally use
that's-
cosine 15. That's right, Emma.
Well, I still got the same answer though. Would I get points taken off?
1 point. Yep. You got the same answer because it divided out.
Well, the thing is that I used cosine of 75 because it just made more sense because that would be because you're trying to find the like the lever, I guess, like the the I forgot what it's called,
The
that
lever
I
arm,
think.
yeah.
Yeah, the lever arm. And it just made more sense to do that, to do cosine of 75.
But
Or it because it kind of worked though.
it worked in this case by accident because all of the angles divided off.
So, but you would, because I drew a picture and I did kind of show why I did it, and I think it still would make sense, but I don't know if you would still take points off for that.
Yeah, so the book, so if you go by the book's formula, torque, the formula for torque calls for the sine of the angle between the lever and the force. And conceptually, you need the part of the force that is perpendicular to the lever because that's the part of the force that's going to be rotating it.
Yeah, so I did. That's what I did. I did cosine to get the x the x value, like for so that the x value could be like perpendicular to the force.
But cosine of 75 isn't the part that's perpendicular to the...
It kind of is. I can.
I'll take a look at your drawing when I grade it, but yeah.
Okay. Thank
Without
you.
without having it in front of me, I can't say anything more.
Thank you.
Okay. So say you have a grindstone here. Does everyone know what a grindstone is? So a grindstone is a hard rock, or and you spin it up, kind of like a potter's wheel, but on its side, and you use it to sharpen knives, basically. So you have this spinning rock, and you put your knife to the edge of the grindstone like this, and it grinds away a little bit of the steel of your knife to make a bevel in your knife, and that's why your knife is sharp. I watch a lot of blacksmiths on YouTube, so maybe I'm more familiar with grindstones than the average person. Yeah, it's a blacksmith thing. I mean, there are modern bench-mounted versions that you can use for sharpening, but yeah, these big old-fashioned ones are mainly used by smiths. Well, a kitchen knife sharpener is basically this in miniature. Also, most kitchen knife sharpeners don't work very well. So we're going to exert a force 200 newtons tangential to this grindstone. So we're going to exert it to the right, and initially this thing is spinning, say, clockwise. I meant counterclockwise, spinning in the positive direction. Okay. We're going to need to calculate what the moment of inertia of this thing is. So the moment of inertia of a disk is equal to 1/2 mr squared. So in this case, it's 1/2 times 100 times 0.09. So yeah, this is like 4.5. Once we have that set up, we can say we can use the impulse momentum theorem for rotation. So a change in angular momentum is equal to a torque applied for a time. Right, we are going down, we're going to stop the grindstone, so our change in angular momentum is equal to 0 as our final, minus, and our initial is I omega. We're causing a negative torque on this thing, so negative 200 times 0.3, that's the torque. Right, so force times the distance from the axis of rotation, and this thing is, of course, rotating about its center, times delta t.
Dr. Wolves,
Mm-hmm.
I'm sorry. So for disk, why did you say that the disk is that formula? 1/2. Oh wait, never mind. I'm sorry.
We're okay?
Yeah, I didn't see the 1/2. I'm sorry.
Okay. This takes like a second and a half. You could also have done this with rotational kinematics, but it would have made me sad because we were studying momentum in this chapter. All right. Last problem. The angular momentum of the Earth. So here's the sun. Here's the Earth. I didn't give the magnitude for the torque, but I did give the magnitude of the force that was applied. I'm not understanding what you're asking, Yusuf. Yeah, how long? Like, in time. Yeah. Oh, that's true. What magnitude of torque does this exert? Yep. And then the final question is about time. You are right. You are right. The magnitude of torque is just going to be this much.
Dr. Wolves, I forgot to do that. So how many points would you take off?
Just one.
Okay.
Right, since it's a value that you need for later on in the question anyway. So if you didn't explicitly state it, it's not a huge deal. All right. Sun and Earth. Anyone know offhand what the distance between the sun and the Earth is on average?
I think it's 1.5 times 10 to the 11 like meters.
Yeah.
Okay.
That is correct.
Yay.
At distances this large, the actual shape of the Earth does not matter, and it is approximately a point. This is me not reacting to your troll, Chad. Um, right, on one of these tests, I'm just going to say at the end of the question, give your answer in U.S. customary units. All right. So what is the angular speed of the Earth about the Sun? How do we even figure out the angular speed of the Earth around the Sun? Well, we know that the Earth makes one rotation per year around the Sun. If you Googled it, that is okay, but I mean, I would have liked to see you work out the angular speed. Because there's approximately pi times 10 to the 7 seconds in a year. That's an approximation that's good to within like 3%, I think. So it's a useful approximation to know. if you're an astronomer. The moment of inertia for the Earth around the Sun, right? So the moment of inertia for a point is just mr squared. So we just need to know the mass of the Earth. And everybody knows that it's 6 times 10 to the 24 kilograms. Right, so 1.5 squared is 2.25. 2.25 times 6 is approximately 14. So the moment of inertia is approximately 14 times 10 to the 46. And of course, the angular momentum is equal to moment of inertia times angular speed. So that's going to be 28 times 10 to the 39. If you were doing this, technically scientific notation must be an integer between 1 to 9. Who are you, the scientific notation police? I almost had something better. That that was lame. Okay. For the Earth around its own axis. The angular speed of the Earth about its own axis is 1 rotation per day. 2 pi rads per rotation. And of course, everybody knows that in 1 day, there are 84,600 seconds. So this is 7.3 times 10 to the minus 5. Do not know why you have that memorized? Because I teach this problem every year. Yeah. And I am a nerd sniper. That is exactly correct. You would be shocked at the amount of useless information that I have stored away in the back of my brain. Maybe you wouldn't be shocked because you all think I'm a giant nerd, but some people somewhere would be shocked. Okay, so the Earth is a solid sphere. So we need to look up the moment of inertia for it, and the moment of inertia for a solid sphere is 2/5 mr squared. So 2/5. The mass of the Earth, as before, is 6 times 10 to the 24. The radius of the Earth is 6 times 10 to the 6 meters. Right? And of course, 6 cubed is 216. So we have 2 times 216 times 10 to the 36 over 5. Right, so this is something like 86.4 times 10 to the 36. So then the moment of inertia is I omega, or sorry, not the moment of inertia. The angular momentum is I omega. So we just smush these two numbers together. Where did the 36 exponent come from? Oh, because this is actually supposed to be squared. So when we square the radius, we get 10 to the 6 squared, which is 10 to the 12. And then we have a 10 to the 24 here. So 10 to the 24 times 10 to the 12 is 10 to the 36. All right. And just for Yusuf, 630 times 10 to the 31 is the same as 6.3 times 10 to the 33. All right, that's the whole exam. I think this is probably an excellent place to take a break, stretch our legs, grab some water. My clock shows coffee. Absolutely, I'm there with you. My clock shows 10:09. Let us be back here at 10:20, so 11 minutes from now, and we will give a brief treatment of chapter 12 in the book, which actually there's not that much in it, so that shouldn't be a problem. All right, I will see you all back here at 10:20.
Professor Wolf, I have a question. For problem 8, I tried to use like the L equals I alpha, but for alpha, I accidentally found omega, the wrong omega, because I missed terms while I was dividing,
Okay.
doing the dimensional analysis thing.
Did you say I alpha or I omega?
I alpha.
So I alpha is actually torque, not angular momentum.
But then I just used omega by accident.
Well, I'll have to take a look at it when I get to your test.
Okay. Right. Thanks.